Today I will present collaborative race detection. This is joint work done with my colleague Christian Zamfir and our advisor Professor George Candea at EPFL. So what I mean by a data race is a situation that occurs in multi-threaded programs in which there are accesses to a shared memory location by multiple threads, where at least one of these accesses is a write, and the accesses can happen simultaneously. In other words, they're not protected by synchronization operations. So the problem is that if you look at modern software, there are many data races. For instance, while loading a web page in Firefox, you'll get more than 1,000 races detected if you use a state-of-the-art race detector like Thread Sanitizer. This is in stark contrast with the POSIX threads specification, which has been around for a while, and also the new C++ memory model, which explicitly do not allow programs to have races. The implication of these standards is that compilers can break racy programs in arbitrary ways. Such broken programs cause disastrous things to take place in the past. Humans have lost their lives while being treated by the infamous Terak 25 device, and Northern America was hit by a massive blackout. So if races are so bad, how do we ensure that software ships without races? Well, first we have to detect them, and for that we can use data race detectors. And these detectors come mainly in two flavors: static race detectors and dynamic race detectors. So static race detectors are typically fast, and they analyze all paths in a program. Therefore, they have few false positives, that is, few missed real races. However, their analysis lacks the full path context of actual program execution, and therefore, they report many false positives, that is, false race reports. This causes developers to be overwhelmed by the number of race reports to investigate, and either they end up losing a lot of time, or they simply don't use these detectors. On the contrary, dynamic race detectors detect races during actual program runs using a single path at a time, and therefore they have few false positives. But their analysis is limited to those runs, and thus they have many false negatives. So even if developers use these detectors, they cannot have enough confidence that their program will become race-free once they fix those races. So also, these detectors typically monitor all memory accesses and thus tend to be slow, which is another factor impacting their usability. Bottom line is, existing detectors have important limitations that need to be overcome. Ideally, what we would have is the best of two worlds. That is a race detector that performs full path analysis, that has few false negatives like the static race detectors, and that has few false positives like the dynamic race detectors. In this talk, we introduce collaborative race detection and our prototype system called CORD that we built to achieve these goals. The key idea in CORD is to statically detect potential races and dynamically validate them. That is, to determine whether they are actual real races. CORD effectively detected 8 real races in 2 real programs with 1% average runtime overhead. Okay, so CORD engages all programs running, all computers running some program P into a cooperative effort to automatically detect races in that program. CORD is meant to be a global, distributed cooperative of laptops, tablets, smartphones, and even game consoles. Developers use a central component that we call the hive to statically detect potential races in a program P. The hive then crowdsources the task of validating these potential races to the pods, where the users run their programs. By validation, we mean determining whether these potential races correspond to actual real races. The validation tasks are split among the pods to ensure low overhead. Users run their software inside pods, which relay validation results back to the hive, which then processes these results to identify races in the program P. What we're trying to do here is to leverage the power of full path analysis of static race detectors at the hive and leverage the full path context of dynamic analysis at the pods. So CORD is based on the observation that computer users today have overwhelmingly more hardware than any software company has. Just think about it. Today, Google's Chrome web browser runs on 300 million computers. This number exceeds by 2 orders of magnitude the most optimistic estimates of how many servers are housed in Google's data centers. Furthermore, last year alone, consumers bought 1.8 billion mobile devices. That is 3 orders of magnitude more units than in 1 year, compared to servers accumulated by Google in 14 years. Even if not all the users are willing to participate in such a crowdsourced effort to make software better, there's an increasingly large number of beta testers for modern software. For instance, Windows 7 had 8 million beta testers. Users execute their software billions of times around the world every day. And today, the potential to use these executions to improve software is great. We believe that it's the right time to leverage the ever-increasing hardware resources of users. And Cord is an initial attempt to achieve this goal. OK, so we said that the Hive is the place where static race detection takes place. The algorithm that we use to statically detect races is a variant of the popular lockset-based race detection algorithm from the RacerX paper. I will now describe the high-level operation of the algorithm. For this, let's assume that the control flow graph of the program for which we want to detect races looks like the following. The race detection algorithm that we use is top-down, meaning it starts from the entry point of the CFG, and it performs a depth-first traversal of the CFG. The analysis is also interprocedural, meaning the analysis is extended beyond procedure boundaries and calling contexts are taken into account. The analysis also follows program flow and paths rather than, say, conflating the effects of paths at join points in the CFG and thus losing context. OK, so now let's go over a simple example to see how log sets are actually tracked during this algorithm. So imagine that we have a global variable x in our program, and let's say that a certain thread follows a certain path through the program, which is denoted by the blue path here. And in that path, the variable x is set to 1 while being protected by a lock L. And then another thread follows another path through the program, the red path here. And in that path, the variable x is set to 2 while being protected by a lock K. Cord's static race detector keeps track of these accesses along with the log sets at the moment these accesses occur. So the log set in path 1, while x equals 1 executes, has the lock L, whereas the log set in path 2, when the statement x equals 2 executes, has the lock K. So then Cord's static race detector checks to see if any two accesses to the same variable might have occurred while not holding a common lock. For this, the detector computes the intersection of lock sets for any two accesses. And if the intersection is empty, such as in this case, it flags a race. To summarize, the detection algorithm that we use is top-down, flow-sensitive, interprocedural, lock set-based static algorithm. This algorithm is one of the few ones that scale to systems with millions of lines of code. Now, this race detection algorithm is fast, but it has false positives. And the main reason for false positives is that it only keeps track of locks and may mistakenly flag races because it's unaware of some synchronization operations like semaphores, user-defined synchronization, or condition variables. So therefore, the races detected by this algorithm are only potential races. That is why we crowdsource the validation of these potential races that are statically detected in the Hive to the pods. Each pod is responsible for validating a small number of races to reduce the overhead. Validation phase essentially tries to determine whether there is an ordering relation that the static race detector missed. So previously, the Hive detected a potential race between the two writes to the variable x. And now, if these accesses are actually indeed racing, they can be executed in any of the two possible orders. And to see whether this is the case, the Hive instructs the pods to enforce each one of these orders during program execution. So what the pod 1 will try to do is to get the instruction x equals 1 executed before the instruction x equals 2, and vice versa for pod 2. Then the pods will relay their findings back to the Hive. So it might be the case that both orders of instructions get executed, and then, therefore, the Hive will decide that there is an actual race. Pods are also capable of determining whether the program crashes or deadlocks, and relay back this information back to the Hive. The program may deadlock in one of these executions, and in the other execution, the program just may execute normally, in which case the Hive will decide that there is a race, and this race actually causes a deadlock. The same thing applies for crashes. So the two accesses are executed, but one of the orders of the accesses caused the program to crash. The Hive will decide that, yes, there is a race, which is causing a crash ultimately. So if one of the orders is only executed and the other one is not observed, the Hive will think that this race report is a potential false positive. It might also be the case that these accesses are not executed at all. So we built a prototype system and evaluated it using two real programs, PBZip and SQLite, using some of the developers' tests and tests written by us. SQLite is an embedded database with 100% branch coverage with developers' tests. It's used in iOS and Android, and PBZip is a parallel variant of the bzip2 compression tool. So Cord detects 88 potential races in SQLite and 122 potential races in PBZip. Out of these potential races, it turned out that one of the races in PBZip is actually a real race, but that does not have any observable consequence like a crash or a deadlock. In the case of SQLite, there were 4 races that were causing SQLite to deadlock, and in the case of PBZip, there were 3 races that were causing PBZip to crash. For both programs, there were a considerable number of likely false positives. So nearly half of the races detected by Cord were actually classified as likely false positives by the Hive. Also, some of the racing accesses were not executed at all because of the limited number of test cases, which was 10 in our case, that we used in our preliminary evaluation. The runtime overhead of Cord is below 1% for both programs. And in summary, Cord was effective and low overhead at detecting these races. We also compared the efficiency of Cord to dynamic race detection. For comparison, we used a state-of-the-art race detector from Google, namely Threat Sanitizer. We can see that the runtime overhead of Threat Sanitizer is 3 orders of magnitude higher than that of Cord for both programs. It's also important to note that a static race detector that used the same algorithm as Cord would have discovered the same number of races, but it would have more false positives and wouldn't have provided a classification like Cord is providing. So we believe that the benefit of tolerating the low overhead of Cord in a production system is that race detection results end up being more detailed and more helpful. In summary, we presented collaborative race detection and our prototype system, Cord. Cord is effective and efficient, and we see great potential in Cord in particular and in crowdsourced improvement of software in general. Developers will buy more time to develop new products and features because they will spend less time debugging, while this collaborative effort will help them make their software better. Better software will in turn mean that users will have access to higher quality software. Finally, I'd like to mention a roadmap of ongoing and future research. We're thinking of synthesizing fixes at the Hive and distributing them back to the pods to make sure programs don't encounter the future occurrences of races. This system also obviously comes with privacy implications, and we're exploring general ways to quantify the balance between the amount of privacy leaked from the pods back to the Hives and the amount of execution information. Finally, we want to extend Cord to other types of bugs like atomicity violations. This brings me to the end of my talk. I'd be happy to take your questions. So the way we simulated this is, so we used about 200 nodes to simulate this thing. So it doesn't use actual users of to actually validate these results, but the way we simulate it is like using 200 nodes. Yeah.
It was partly just that number, the overhead number was interesting to understand. So I've got like 200 nodes each running
Yes.
101%.
True.
Arguably that's bigger overhead, but I mean it's for free, I guess.
Yeah. Thanks.
I guess, going back to this, what's a good metric for figuring out how free other people's computation is? Because if I look at this from, let's say, an energy usage perspective, right? I look at this in the sense of, well, this is just, this is just pennies on a large amount. This is just a very small amount. It looks pretty good. Do you have any idea about what a good metric would be for evaluating? It seems like 0 is probably wrong for other people's computation, and it should be some small value, but what should one pick?
Okay, that's a good question. So I guess, well, considering energy might be a good metric. Like the amount.
But it's probably bad for you.
For us, it will be bad. So on the other hand, we didn't evaluate to see, we just only evaluated the runtime overhead. So it's unclear how this affects actually the energy spent. And therefore, I cannot really say anything about that. But yeah, I guess to users, what seems more relevant is the lag that they will experience, the runtime overhead. So therefore, if we are more user-centric, I think considering runtime overhead is a good metric. That's why we did that. Throughput is also another important thing.
So I had a question. I was wondering whether your approach would not incentivize software makers to release buggy code. If you think about it, what you're proposing is that you have the static analysis phase that says, here's some things that look like a bug. I'm not sure if it's a bug or not. Release this stuff, let the crowdsource and decide if it's a bug, right? Wouldn't that create the wrong incentives for software makers to release these buggy projects to the community?
Yeah, yes, that's a good question. So the problem is the static analysis phase will normally output lots of potential bugs, and it's hard for a developer to go through each one of these and investigate whether it actually corresponds to a real race or not. So this is why we leverage the users to actually gather this information and to see whether it's corresponding to a real race or not. So I don't think it will incentivize people to release buggy software, but it will actually increase the quality of software over time when it's executed over time. So, yeah.
But I mean, if you're faced with that dilemma, like something looks like a bug, but I'm not sure, release it and let the crowd decide, right?
But
isn't that the attitude?
But it depends on the number of these things, right? So if you end up flagging thousands of potential races, so you're faced with the dilemma of whether they're actual races or not, but it's not really possible or feasible to go through each one of them and try to see whether it is a bug or not. And that's yeah.
So just a curiosity, is separate from your work. Do you see any implications of the choice of language for the type of bugs and these kind of races or races?
I think there is a. So the way we targeted this, so we targeted C and C++ programs, and actually we targeted an intermediate language called LLVM, and programs that can be compiled to LLVM can actually work with our prototype now. But the choice of the language, whether it's statically typed or dynamically typed, for instance, might have an effect, especially on the number of false positives. So if the language is statically typed, for instance, you have more type information, and therefore you can probably reduce the number of false positive reports in static race detection. Whereas if you have dynamically typed languages, you probably will end up having more false positives. So it will impact the.
So supposing you were designing a system where you would like to have a lack of races, could you propose a certain type of programming structure that could facilitate reduction of races by design?
So you can use different programming models for that. So probably you can use message passing based things or other programming models. But this work actually targets mainstream languages and programming environments. It's always an option to change the programming model, but that's a dilemma. It's an open dilemma. Yes.
So I was wondering, like, why is the mostly to reduce the overhead of finding the bugs, people actually look into only the synchronization schedules, because your static analysis tool is trying to target only the synchronization operations. Right?
Yes.
Now there's a more robust way to do is to track the individual shared memory accesses as well, which is called memory schedules as well, right? And since you have the crowdsourcing, so what I was wondering, like, in addition of keeping track of synchronization of constraints, you can also keep track of memory accesses as well, which are not synchronized, for instance. And you can push this more information to the crowd and then let them give you more insights about how to detect bugs, because now you have even more resources to do this tracing and try to find dynamically which are kind of benign and which are harmful. So you have any thoughts about that, how to do it in more robust fashion when you have information about synchronization schedules as well as memory schedules?
I see. So it certainly can be leveraged if this is not going to impact the way people use their software, right? In terms of the overhead that they experience and whatnot. So this is, yeah, certainly combinable. Yeah.
I have another question regarding the exponential space explosion. So I think
Yes.
your premise is that if you send stuff to the crowd, you have 2 or 3 orders more resources in order to be able to find those places to see if they're really true or not.
Yes.
But you still fundamentally have a problem of exponential blowing state space, and 2 or 3 orders of magnitude may not cut it when you have millions of lines of code, right? So why is it the case that you are able, just with a constant factor improvement of like 1,000, be able to find things that you can't find in the simulation?
Yeah, so that's probably correct. But so the only resource that we know that also exponentially increases, that matches the increase in software's complexity is the hardware resources of the users. Although the trend may be different kind of exponential, but this is kind of the only resource that matches that. So that's why we wanted to target this. Yeah.
Any more questions? Thank you.
Thanks.